Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video, we're going to take a look at area between curves. In the previous video, we talked about the definition of area between curves using integrals, and we did our areas using vertical rectangles. We defined area in terms of finding the integral from a to b of the top curve minus the bottom curve. However, sometimes you're going to have situations where it's preferable or even necessary to use horizontal rectangles rather than vertical. Let's take a look at this example. If we wanted to find the area of this region right here, we could use vertical rectangles, but you'll notice that this is basically divided into two separate areas. The way I would describe the length of the rectangle in this portion would be that curve minus this curve. And the way I would describe the length of the rectangle in this portion would be that line minus that line. So in situations like that, I would probably use a horizontal rectangle where I could describe the whole region with the same rectangle. If we took a look at this example, if I wanted to find the area of this region, I would not be able to use vertical rectangles because if I took the top curve minus the bottom curve, it's the same curve, so I wouldn't be able to do that. In this situation, it would be necessary for me to use horizontal rectangles. So let's define how we find the area of a region using horizontal rectangles and do some examples. When we use horizontal rectangles, we're now going to do everything in terms of y instead of x. So the function that's going to be on the right is going to be a function of y, f of y. The function on the left is going to be g of y. So our right curve will be f of y, and our left curve will be g of y. In addition, instead of using a, b as our lower and upper limits, we're going to use the letters c and d. So what we're going to do is take this representative rectangle and define its area. So the length of this rectangle will be this x value minus this x value. So the way that we describe this x value is f of y. So f of y will be this whole distance, and then this distance here will be g of y, the x value for that function. So if I take f of y minus g of y, that will give me the length of that rectangle. The width will be dy. And if I want to find the sum of all of those slivers from c to d, I use integration. So my area will be the integral from c to d of f of y minus g of y dy. Let's take a look at an example of using that. So we're asked to find the area of the region bounded by y equals x cubed, x equals 4, y equals 1, and y equals 8. So our first step is to draw this. So y equals x cubed looks like this. X equals 4 is a vertical line. Y equals 1 is a horizontal line, and y equals 8 is a horizontal line. So the region bounded by those four curves, although some of them are actually straight lines, would be this. There's a whole bunch of regions in here, but be careful that you find the region that's bounded by all of the curves that you're given. So this is the area we want to find. As mentioned, I could use vertical rectangles, but then I have to split it up into two areas and find the areas separately and add them. Or I can use a horizontal rectangle. Now, we've already got this as a function of y. We've got x isolated. This one is y equals x cubed. If we want it as a function of y, we have to isolate the x. So x would equal the cubed root of y. Or in other words, x will equal y to the 1/3. So that's my function of y. In order to set up the integral, I need to know c and d. I need to know the y values with my limits. So it's going to be 1 to 8. And it's going to be the right curve, because it's this x value, which would be 4, minus this x value. This x value will be y to the 1/3. So that would be the length of that representative rectangle, and the width is dy. And now we integrate. Whatever your variable is, you integrate the same way you do when your variable is an x. So the integral of 4 dy will be 4y. The integral of y to the 1/3 dy will be y to the add a 1, so that becomes 4/3. Take this coefficient of 1 and divide by 4/3, so we get 3/4. And now we evaluate it at 8, evaluate it at 1, and subtract. So the area would be 4 times 8 is 32, minus 3/4 times 8 to the 4/3, that would be the cubed root of 8, which is 2 to the 4th power would be 16, minus 4 minus 3/4 times 1 to the 4/3 is just a 1. This would simplify, the 4 would cancel. It's like 16 over 1, so the 4 would cancel, and this would become 12, so 32 minus 12 would be 20. Minus 4, minus minus gives me plus 3/4. So that would be 16 plus 3/4, which would be 16.75. That works out to a nice even decimal, or 67 over 4 square units. When it works out to an even decimal, you can go ahead and do that. But if it's not an exact value, I would probably leave it as a fraction. So it's a very similar procedure, but now you have to think of everything in terms of y. Your values on your integral are the y values, and you have to write everything in terms of the function in terms of y, not x, and it's dy. Let's take a look at another example. In our second example, it asks us to find the area of the region bounded by x equals y squared and x equals 4. So let's draw those two curves first. So x equals y squared looks like this, and x equals 4 is a vertical line. So what we're finding is the area of this region here. We have two options for finding this area. If you do want to use vertical rectangles, you can't describe that whole length as the top curve minus the bottom curve, because it's the same curve. But because of the symmetry, you could find the area in quadrant 1 and then double it. We'll do this question using vertical rectangles, and then I'll redo the question using horizontal, so you can see how it's done differently, and you can see that the result will be the same. So if I do this in terms of x, I need to write this curve in terms of x. So if x equals y squared, then y will equal the square root of x, the top curve here, or x to the 1/2. I've got my a and b value, 0 and 4. I don't need to calculate my points of intersection. So what I'm going to do is find the area under this curve, so above the x-axis, from 0 to 4. And then I'm going to multiply by 2 to cover this region here. So it'll be 2 times the integral from 0 to 4 of x to the 1/2 dx. Okay, or minus is 0, the bottom curve is 0. So if we integrate this, we're going to get x to the 3/2 divide 1 by 3/2 to get 2/3. So that will be 4/3 x to the 3/2. And now I evaluate it. When I put a 4 in, square root of 4 is 2, 2 cubed is 8. 8 times 4 is 32 over 3 square units. This question was possible to do with vertical rectangles, but you had to do one region and double it, but that only worked because we had the symmetry. If the symmetry wasn't about the x-axis, you wouldn't have been able to do that. In that case, you would have had to use horizontal rectangles. So let's take a look at how we would evaluate this area using horizontal rectangles. If I'm using horizontal rectangles, I can still use the symmetry idea. I can just find this top half and double it. So I'm going to do that. But I need to know this value here. So I need to know these points of intersection. So the points of intersection when the x values are equal. So when y squared is equal to 4, so y will equal the positive and negative square root of 4. So positive, negative 2. So I'm only going to focus on the top half and double it just like I did there. And to find this area, I'm going to go from 0 to 2. And because I'm doing everything in terms of y, I'm going to take f of y, or the right curve, which is 4, minus the left curve, which is y squared. Remember, it has to be in terms of y. When you're using horizontal rectangles, everything has to be in terms of y. dy. So my length is 4 minus y squared, and my width is dy. Now I integrate this. So the area will be, this integral will be 4y minus 1/3 y cubed. And now I evaluate it. 4 times 2 is 8, minus 2 cubed is 8, so 8/3. That's 24/3 minus 8/3 will be 16/3. So my area is the same using either method. So when you're asked to do these questions, what I do is I look and see, is it easy to use vertical rectangles? Because students typically are used to working in terms of x. So look to see if it's easy enough to do it with vertical rectangles. If it's not easy, if it's divided into different regions, or if it's impossible, then look at horizontal rectangles and then think of everything in terms of y. Do as much practice with finding area between curves as you can. The more practice you get with that, the easier you're going to find the next topic, which is volumes. Take care, and we'll see you on the next video.